This video is going to focus on voltaic cells. It's important to note that voltaic cells are sometimes called electrochemical cells, or sometimes you'll see them referred to as galvanic cells. So all of these names are equivalent. Voltaic cells are used to generate electricity from chemical reactions. And what happens is the redox reaction takes place within the cell, and that produces a flow of electrons, which produces electricity. A voltaic cell consists of three separate pieces or components. First are two half cells. We'll talk about what a half cell is in a minute. The second is a salt bridge that connects the two half cells. And finally, wires that connect the electrodes to a voltmeter so that we can measure the voltage. The two half cells then are made up of a variety of components. So each half cell, what we do is we set them up basically in a beaker. So you're going to have a half cell that's made up of a container, pretty typically a beaker, if we're doing it in a lab situation. The other component is the substance in its solid elemental form, which acts as the electrode. So this would be the solid form here. Say, for example, this is a piece of silver. Now, these electrodes can either be positively charged or negatively charged, and we'll come back to this when we come to setting up the cell. The electrode where reduction occurs is known as our cathode, and that is labeled with a positive sign. Our anode is the electrode where oxidation occurs, and that is given a negative sign. The third component of a half cell is a solution of the substance in its ionic form. So its ionic form for silver would just be Ag+. Pretty typically, this is a nitrate solution. So this would most likely be silver nitrate. And they use nitrates because they're soluble, very easy to make up in solution. So it makes a really good solution to use in voltaic cells. In terms of the salt bridge contains a saturated solution of some sort of inert salt, so something that's not going to react in our redox reaction. There are four pretty typical ones that we use. So sodium nitrate, sodium perchlorate, potassium chloride, or potassium nitrate. Here's an example here then of a setup of a copper-zinc voltaic cell. So when you're given a question like this, where you're asked to set up a voltaic cell for a certain pair of metals, the first thing you want to do is look at your chart, so page 12 of the data booklet, to determine which out of the copper or zinc is going to undergo oxidation and which one's going to undergo reduction. So you're looking for the combination that's going to give you a spontaneous reaction. In terms of these two, copper is going to act as our oxidizing agent. Zinc is going to act as our reducing agent. That means that copper is going to undergo reduction, and reduction happens at the cathode. You can remember this with the acronym RED, CAT. That means that our reducing agent, our zinc, is going to happen at the anode. So we have oxidation happening here. If we write the half reaction of our oxidation, zinc solid is going to go to zinc 2 plus 2 electrons. And that's aqueous. Okay, that is our oxidation reaction. And then our reduction reaction, copper 2 plus aqueous plus 2 electrons is going to give copper, solid. All right, so this is our zinc electrode and our copper electrode. The solution then is likely, in this case, let's just take it as zinc sulfate. So sometimes they're also sulfates. And we'll take this as a copper sulfate solution. Usually you'll be told what one to use for your particular example. Now, to look at electron flow here, zinc is giving up 2 electrons, and copper is gaining 2 electrons. So the electrons are going to flow from the negative to the positive, or from the anode to the cathode. We want to show that electron flow with arrows on between our 2 electrodes. We also want to show what's happening with the ions. So here in our anode, zinc solid is being transformed into zinc 2+ ions. At our cathode, we're taking copper 2+ ions from solution and turning them into solid copper. Over time then, what you're going to see is this electrode's going to get eaten away because it's using up the solid zinc to make the zinc 2+. At this electrode, you would see a deposit of copper because it's taking copper from the solution and creating solid copper. The last thing that we need here is to talk about the salt bridge. So like we said before, this is usually an inert salt. Let's take, for example, our salt here is potassium nitrate. Now, at our cathode, we are losing our positive charges because they're being transformed into solid copper. So the positive ions of the salt in our salt bridge is going to come into this solution and try and restore the charge. Similarly, on the other side, we are depositing positive ions into the solution. So to neutralize that charge, the negative ions of our salt bridge are going to flow that way in order to establish and make sure that those charges do not become too unbalanced. The last thing we want to do with these is include an overall balanced chemical equation. So in this one, zinc solid, you can write in solid there, I'm not going to, plus copper 2+ is going to react to give zinc 2+ plus copper. Now the last thing we need to do is, I'm just going to show you a shorthand notation for Voltaic cells. So for the one we were just doing on the previous slide, the shorthand notation for it would be this. And what we normally do is we list the anode first, the cathode second. Each single line, like this one here, represents a phase boundary between the electrode and the solution. So this would be our electrode, this would be our solution. The double line represents our salt bridge.